Python grammars like the regular expression module and the file manipulation, and also how to define a function and how to write a file, how to open a file, and how to rename a file. And it's these are just some basic operation of Python. And yesterday we Manning talk about the Tensorflow Basics, some important terms in Tensorflow. We talk about the what is tensor, what is graph in Tensorflow, and graph contains a lot of nodes and edges, and what is session, and why when is session, why is fate, and why is fetch. So first, let's have a review of this basic term. So in Tensorflow, the computing process of a TensorFlow of training or creating a machine learning or deep learning model, we usually will divide it into two steps. The first is we need to assemble, or define a graph. So define a graph. So we need to express the computational process or the numerical process, computational process or numerical computation into a graph, or as a graph, maybe as a graph. As a graph, that is the first step. We need to create a graph. We need to define a computational graph, a data flow graph. And then the second step is execution. The second step is execution. Execute the graph to light up some nodes. We need to run a session. We need to run a session and feed input values into the graph, and then we can fetch some output from the graph. So we separate definition of the computation and their execution. The reason why we separate the definition of the computer graph and the execution of the computer graph is for better allocation of computational resources. So that is the name. That is aim. We separate these two steps. So we define a graph, and in a data flow graph, it contains a lot of nodes and edges. It contains a lot of nodes and edges. So nodes in a graph usually represent the operations, the data operations, and the graph edges in a graph are tensors, which flow between nodes, and they can describe some input and output relationship between nodes. So that is some basic term in TensorFlow. And when we start a session, we need to feed the input data. We need to feed the training samples into the model. So here another, we need to feed data into the graph, and to get the output value from the graph, we need fetch the value. That is a fetch mechanism. So today, so maybe we're gonna do some hands-on practice. If you successfully installed TensorFlow and Python, you can follow me. Maybe we can program together. And here, to start a new Jupyter notebook, here, click New and Python 3. So to import TensorFlow, we would use this command, import TensorFlow, usually as TF. So import TensorFlow as TF, and you can check your TensorFlow version. So that is TF under 9. Sorry, under 9 version. And here I'm using TensorFlow 1.30. So if you installed the version of your TensorFlow is maybe version 2 or version 2.0, version 2.1, you can use this command. No, sorry, not compact, but compact. Here, compact, you can use this command to import TensorFlow so the session match, so this session feed and fetch mechanism would work if you install TensorFlow. So if you install TensorFlow, use this command, the TensorFlow 1 would work in your TensorFlow 2 environment. And here we are using TensorFlow 1.30. So import TensorFlow. The first thing we're gonna do is to define some constants. So the first thing, we can change it to a markdown. Here's node, so we can code here. Here's code, so we can program here, and we can change it to markdown, so we can write some contents. That is the definition. Oh, okay, the define constant. So constant. So in TensorFlow, here is the way we define a constant. We use TF TensorFlow the constant, and followed by what is the constant. Maybe it can be int 1, or it can be 2, or it can be a string. Maybe here I will write like hello, not hello word, maybe hello TensorFlow. So here is the constant we've defined, we've initialized, and we can check, have a look of this constant. So here is the output, and it will tell you it is a tensor and it's a constant, and here is the name of this constant, that is const 0, and the shape of the constant is empty because we just define the constant. We just create a computation graph. We just create a graph. So if we want to fetch anything, fetch any value, we need to start a session and get out of this value and start a session, run a session, and then pick up this value. So here the data type is a string. So if we want to have a look of the constant we've created, have a look of the value of this constant, we need to start a session. So here, the basic way to start a session, use sys equals tf the session, and then we can run this session, that is sys the run. We use session the run and which node you wanna pick up, which value, which constant you wanna have a look. So that is session the run, and the node we wanna have a look as hello. This node we've defined, this constant we've defined. So the output will be the value of this constant. So that is TensorFlow 1. We separate the definition of computational graph and the execution process. So if you want to have a look at any value of TensorFlow, you need to start the session. You need to start the session and feed something into your graph, or you can fetch some value of some specific node. So we start a session and we run the session. So after all these process, we always need to close the session. That is stop close. So to close the session, so that is a basic process. First, we need to define the computational graph and then start the session, and then do something, some operations like feed some input value and get some output. So here is a constant, and maybe we can have a look of some other example. Sorry, maybe addition. So how to implement addition, that is a plus b. So for example, a plus b here. So we want to know a plus p equal to c, the value of c. First, we need to define a and b. Here, a and b, we define a and b both as a constant. So the value of a maybe is 10. Let's choose no constant. Yeah, and here b is still a constant, and the value of b maybe is 7. And so, and here the computational process to define a graph. So we got two nodes in this graph, in the graph, the nodes A and node B. So the computation process is node A plus node B equals node C. That is the output node. So A plus B. So here we define. We define two nodes, node A and node B. Node A plus node B at, so the output is C. So here is untitled. So to figure out, to pick up the value of C, we need to also start a session, use sys equal to the session, start the session, and run the session. That is session, the run the session. So the value we want to pick up is the value in node C. So run the session and C. So C, the C node is lighted up. So we would get the final value of C. So that is the addition. We need to define the computational process and then start the session, run the session, and get out of the, and then pick up some, and then check the output value. So that is the same if we want to do multiplication. That is, we define two constants, A and B, and do like E equal to A times B. Or we can maybe do matrix multiplication or inner product or dot product. That is the same. So we will have a look of another example. Maybe, sorry. You click here and 3, it will become like this. So we can matrix, sorry, matrix multiplication. So here we define the matrix 1. So for matrix 1, it's still a constant. It's still constant, and so it's a matrix. So maybe it's 3, 3, and matrix 2, a constant. And we need to follow the rule of matrix multiplication. So here it will equal to 2, yes, and the output will be maybe, that is our value, equal to, so matrix multiplication will be TF dot matrix multiply, that is M1, M2. So that is the computational process. And then we define, and when we start a session, so the basic method to start a session is 6 equal to TF dot session. And usually after the process, after all the operations, we need to close the session. But another more convenient and more commonly used way to start the session is we will use a wait statement. And in this, and TF dot session as 6 within this wait statement. And so in this loop body, in this wait loop body, so the session will be started, the session will be open, or will be always open. When we jump out of this, wait statement, the session will be closed automatically. So here we can check the result. So we can check the result, use session the run. That's the we want to pick up, and we can use print result 1. So here is the result, that is matrix multiplication is 2. These are these very simple 2 examples. We use matrix multiplication and addition. So to explain how to do addition and multiplication in TensorFlow 1, we need to define the computational process and then start the session to run the graph to execute the graph. So what we've defined before are just constant. So for TensorFlow, another usually used data type as variable. So here we want to talk something about variables. So for constant, especially in machine learning or deep learning algorithm, these constants are usually some hyperparameters like the apple, like the batch size, like the epochs. So for variables, usually variables in deep learning or machine learning, especially in deep learning, maybe represent the weights and bias. So we always represent the weights and bias in deep learning, because in deep learning, in neural networks, the aim to train a model is to find some proper value, find the proper value of the weights and bias to minimize the loss function. So at first, before we training, we have no idea about the value of the weights and bias. So the model would try to figure out the proper value of weights and bias during training session. They want to learn from the data and to find out the proper value of weights and bias. So the value of weights and bias are uncertain, so we have to figure out the value of weights and bias. So that means we need to change the value of weights and bias a little bit every time till we find some proper values. So for weights and bias, we usually define weights and bias as variables. So to define variables, usually we would use command like this. So TF, not constant anymore, but variable.
Excuse me?
Yes, please. Yes.
I'm getting an error that TensorFlow has no attribute MTMUL. What could be the reason? On the line number 3 in the input. On line number 3. In 9
Yeah.
on line number 3.
So you got arrow TensorFlow has no.
This one. What is this MTMUL?
Matrix multiplication.
Yeah. So what? So it is. Is it?
Excuse me. It is MAT, not MT. MAT.
MATMU. MAT matrix. MUL multiplication.
Yeah. What is MU? Is it MUL or MU1?
MUL multiplication. Times MUL times.
Okay. Can I share my screen to show you the error?
Maybe no. You can maybe screenshot and send me the email, cause
Okay.
Okay, that is MT. Oh, okay, I will write down. That is TF the much. So that is MATMUL. So MAT means matrix, and MUL means multiplication. Yeah. So that is MAT.
Can I send you the screenshot on the WeChat?
Yes, you can.
Okay.
So here we will continue to talk about variables. So for variables, usually we will define the weights and the bias, what we're gonna train, what we're gonna change the value during the training process, which we're gonna change the value during the training process as variables. So to define variables, we will usually use the command like, for example, not B anymore, but maybe var1. Variable 1, the first variable equal to tf the variable. And for variables, so we've mentioned about that for the first time when we create the computational graph, we have no idea about the value of weights and bias, but usually we need to give the weight and bias initial value. We need to give it an initial value. So here we give it an initial value that is 2. So that is initialization. So here name, and usually we will give the variable a name. So that is the name of this node. So this is a node. The name of this node, maybe give it a random name, maybe taste. var taste variable, and we can run this. We need to just ignore this warning. So here we define a variable, and the name of this variable is var1, and name of this node is taste var. So to pick up, to have a look at the value of this variable, we always need to start a session. So also we will use wait statement to start a session. As TF, sorry, start a session, and within this loop, the session will always be open. So here we define a variable. Maybe we can check about this variable. And so if we don't start the session, we can only get the information like, okay, this is a variable, and the nodes, the name of this node is taste variable 0. This is the first variable in this node. And here the shape, no idea, and the data type is float 22, and it is the reference data type. So here we start the session to check the value of this variable. So here we start the session, and when we define a variable, we give it an initial value. So as soon as we define a variable, we start the session, and the first thing we're going to do is to use this command. First thing we're going to do is to start the initialization process. That is to use session the run to make the initialization work. TF the. Here we're gonna use global variable initializing. There's no arrow. Yeah. So this command are used to start the initialization process, make the initialization process work. So here we initialize this variable, and we can check the value of it. There's no global. Wait a second. Oh, sorry.
Variable 1.
Variable 1, no, not B, yeah. TF decision as with TF decision as they start run and then TF global initialize and print. Wait a second.
For me, it worked. 2.0.
Really?
Yeah, it is working for me also.
Maybe you can restart your kernel, it might work then.
Maybe I will try to restart my kernel. Weird. Okay, we will try again.
Can you please check the spelling of session? Session start with capital S or with small s?
Capital S. I'm sure that is TF dot capital S session.
Okay.
Yeah, maybe it works this time. No, cannot be converted into Tensor.
No, just use the tf.global variables initializer.
Yeah, it works. I need to add parentheses followed by the initializer. So that is the same. We can move this into this. So for variables, we define variables. When we start a session, the first thing we're going to do is to make the initialization process work. So that means we need global variables initializer. So here, after that, we can pick up the value of any variable. So here is the example to define a variable and check the value of this variable. And for deep learning models, usually we will define weights and bias, the parameters we want to train during the training process. The parameters we want to adjust during the training process as variables. And for deep learning models, and usually some hyperparameters, and maybe later after the TensorFlow part, we will go into the machine learning part, and maybe 0 we will extend why is hyperparameter. But for hyperparameters, we will usually define hyperparameters as constant, and these weights and bias in deep learning as variables. So here, so when we define variables, we should always remember to initialize these variables, give it some random value.
Excuse me, can you please tell how the weights and bias are working in backend, like in neural networking, like neurons?
Pardon, you mean how Python or TensorFlow working in?
No, I am talking specifically about variables, as you have told weights and biases. and same like weights and biases, neurons and variables work. So I am talking about this. How can you elaborate variable one backendly working? How?
Yeah. Maybe later we will have a view of some example.
Okay, thank you.
Yeah.
Can you please rename your name as well, since I can see your name as Galaxy J6, so that we all know who is speaking at the moment. So kindly rename yourself.
Okay. I'm so sorry. I will rename my.
No problem. Actually, I have to mark the attendance, and on the basis of this attendance, so if you have 80% of attendance, you will get an opportunity to pass our certification exam. We'll give you a free voucher. So I need to mark the attendance also. Thank you.
Okay. My name is Humaira, but let me rename my name. Humaira.
Thank you.
You're welcome.
Kelsey, your microphone is muted, I guess.
Sorry. So we've just learned about constants and variables, and maybe next what we're gonna learn is another term here. This term we call it placeholders. So for placeholders, it's just like it's a placeholder that is here is a note, and for now when we define the graph, I will tell the computer here's a note, and usually the placeholder note will be the note for input data. So when we start the session, we will put the input data into these placeholders. So maybe we can have a look of some examples. For example, here we got our first input, maybe that is input 1. And to define a placeholder, we will use grammar like this tf the placeholder, and the data type, maybe we will use the default data type float, maybe 32, and the value of this placeholder maybe is list 3 2, and we can maybe here we got another placeholder. Maybe here the value of this placeholder data type is still. You can follow me step by step. So sorry. Oh, can you see this stupid? Okay. And we define 2 placeholders, and the initial value of these 2 placeholders are both lists. So here we can placeholders fit and finish. We will talk about placeholders fit and finish, these 2 materialisms. So first, we also need to start a session. So we will use wait statement tf the session, the capital S session as sys, and then we use the run. So first in the first list, so this is there is two things we need to input. The first element is a list. So inside the list, you need to identify which node, which node you wanna check. So here we wanna check the value of maybe, sorry. So we got input 1 and input 2. We need to define the output. So maybe the computation process, maybe the output. The output maybe that is here the multiply input. Input 1 and input 2. So that is the computation process. Input 1 times input 2. And here, what the output value we want to check is the value in the output 1 node. So here we would type, okay, we want to check the value of output 1. And here we got two placeholders. The first one is input 1 and the second one is input 2. And at the first time, the initial value of input 1 and input 2 are both to a list 2 and 3. If you want to give these two placeholders some new names, some new values, so we can use the fit. We can use this fit mechanism. So followed by the list, the second element, the second argument will be list dict. So we will fit the value into fit. That is, so for placeholder 1, so for placeholder, this input 1 is the first placeholder. Maybe we will change the value of input 1 into another matrix, maybe 1, 2, 2.
I think it should be output.
We
line number 5.
Number 5, 1, 2, 3, 4, 5. Yes, station the wrong. Fit dict, and we use a dictionary. We will use key value pair. Yeah, and yes. So the first, we will change the value. Oh, sorry. Okay, here it. Use print. So here is the output. Here is the output. So we got placeholder. So for placeholder, usually for constant, the shape of the constant cannot be changed, and the for placeholders, this just like a container to we can input the input value. We can put the input value into these placeholders. Use the command like this, the finch dict. So finch dict actually is a dictionary. Here, this is a dictionary, and it contains a lot of key value pairs, and so the key is the name of the placeholder, and the value is the value of this placeholder you want to input. And here the first list is the node you want to check. So that is So that is a placeholder, and maybe you can try here. We can have a look of another example. Maybe here we got input 3. Sorry, input 3. Maybe you can define. We can have a look of another value, and it will be more clear. And here input 3 is as a float, and at this time I will not give the placeholder initial value. So here we give it initial value that is at least 2 and 3. Here for input 3 I will not give it any initial value, and we can define some other nodes, like maybe here's a node name maybe is B, and this time the node is a constant. So the value of B maybe is 2, and here constant, another constant. So the value of C maybe is 3. And next we're gonna define our computation process. Maybe first we wanna do C plus B. So C plus B, maybe here is a temp as a temporary. So we will do C plus B, that is addition. That is to do addition, TF add, and B and C. So TF add, and so, and then for input C, maybe that is the out one, and maybe that is temp. We will do multiplication. We will do temp times input 3. That is here multiply. Yeah. Input 3 with. So the computational process is here. I will write down here. That is B plus C and times input 3. So that is a computational process. Hope there's no error. Wait a second. Yeah, it is a placeholder, and this is a constant. This is a constant in TF dot add B and C, and out equal to TF dot multiply. Input Y multiply int cannot. So, okay. We change the data type of the placeholder into int, and there's no error. So we start a session. Also use wait statement as. You can follow me step by step. And then what we're going to do is maybe here get the result. We define the result and use also system run. So the list, the element in the list should be the node you wanna check out. So here I wanna check the value, maybe is the out one, that is the final output. And also I wanna check the value of the temp. And that is, I want to check a value of B plus C. So I want to check value of 2 nodes. So next we're gonna define the data we input. So here we got one placeholder, that is the input C. So for input C, there's no initial value, so we need to feed the input value into input C node. So input 3 node. So for this input 3, the value may be 4. And then we can print, the result. Okay, so here is the result. So what we do is 5 plus 2. Here is 7, and times 4. 7 times 4, 28. So that is the process. That is the fetch placeholder variables and constant. So maybe we will have 10 minutes rest, and then we will continue to talk about some basic grammars about TensorFlow, and we will talk about how to create a model and how to save a model, save the weights, save you've trained. So 10 minutes break. And
in 8, line number 5, can you go to the end of the line?
Okay, here is the end of 9. That is an input value of input node 2, input value of node 1.
Okay, I don't know, I'm getting some error, but okay, I'll check. Thank you.
Okay, thank you.
गोभी बिरयानी 5 रुपए पाव क्या हुआ है गोभी बिरयानी 5 रुपए पाव बिरयानी बना रहा है नहीं पता बिरयानी बना रहे हो आप आपने बोला था मैं बिरयानी बनाऊंगा अभी जुम्मा नहीं हुआ अच्छा आलू की आलू की बना ले बल्लू आलू की बना ले बल्लू आलू की बना ले बल्लू 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 बल्लू
माइक माइक बंद कर दें ये साकिब हुसैन साहब
So now we may continue to talk about some basic grammars of
Hey, Kelsey,
TensorFlow. Yes, please.
will you please provide us with Python experiment files of last 2 lectures along with this Python file also?
You mean send these Jupyter notebooks to you?
Yeah.
Oh, okay. After the class, I will send these Jupyter notebooks to you guys. Okay.
Okay,
I
thank you.
will write down. Okay. Okay. We first review of what we've learned. So first, we talk about how to define constant, and if we want to check the value of the constant, we need to run a session, and in the session we can execute, we can check out the value of the constant, and we use some very simple examples like how to do addition, how to do matrix multiplication in TensorFlow, also define two constants and define the computational process that is C equal to B plus A. And then we start a session, and then we use 6.run. So followed by the note you want to check. So that means the data would flow from the input node to this node, that is the destination node. Okay, so for matrix multiplication is the same. So, and then we talk about variables and weights. So usually we will define, no, not variables and weights. We talk about variables. Usually we will define variables and weights. These kind of values we want to train during the training process as variables. So the grammar to define variables usually like this: tf the variable, and then give it some random value, and then the name of this variable. So here we define a variable, and when we defined a variable, initialized a variable, when we start the session, the first thing we need to do is to make the initialization work. That is, we will use initializers. Here we will use global variable initializer to initialize this variable. So officially, this variable got an initial value that is 2. So we also can use 6.run to check this variable. And then we talk about placeholder. So for input node, so usually in machine learning and deep learning models, we will define the input node as a placeholder. So we can, we then during the sessions, then in the session we can input a lot of samples, a lot of values into this placeholder, and the the data in this placeholder would flow from the placeholder to the final destination, that is here. So we define placeholder. Here is the way to define placeholder, TF the placeholder, and the data type of this placeholder. It can be float 22 or int22, float 34, and you can give it a value. You can assign a value or not. It depends on you. And here we assign the value of this input 1 into a list here, and then we start a session, use wait statement to start a session, and then says the run. First thing we need to identify is the node you want to check. Where is your destination? So here the node we want to check is the output 1. That is the output node. And here for placeholders, we need to fit values into these placeholders. So here we fit values to matrix into input 1 and input 2, two placeholders respectively, and then we can print the value.
We already provided the input values in line 1 and line 2, so why are we allowing putting these values in?
Yeah, you can, for example, here maybe because the input data would change, the training samples would change, it will be different samples, different training data.
I think in the line first 1 and 2 we provided the matrix dimensions, 3 by 2 matrix, both.
3 by 2 matrix.
Yeah.
Oh,
3
okay.
rows, 2 columns.
Sorry,
And
sorry. It's a matrix. That is the shape of this placeholder.
yeah.
So sorry. Thank you so much. So
Okay.
for modify me. Yeah, that is.
No problem. Thank you.
Thank you so much. That is the shape. Yes, it is the shape of the placeholder. That is 3 by 2.
Yeah, I got it.
Okay, thank you so much. Sorry for the mistake. And so another example, we define placeholder and the computational process B plus C times input 3. Input 3 is a placeholder, and here we also can use session with statement to start a session the run, and the output node is the node we want to check, and we wanted the value of out 1. We want the value of temp. So here there is a placeholder, and we can fit value into the placeholder. Here we fit the 4 into input 3, and we can check the value. So next key point we want to talk about is how to save models. So usually the training process will spend us a lot of time, especially for models in computer vision or natural language processing or signal processing, signal recognition. We need speech recognition. We need to there's loads of data. There's large amount of data, and the model is very complex, and we need to spend a lot of time. It requires a lot of time to make the model work in training state. So as soon as we find out we are satisfied with you are satisfied with your model in training dataset and also test dataset, always remember we need to save our model. So next time we can use the model directly. So we can use the model directly. We don't need to train the model again. So here is some grammars for save models, save the structure of your graph, save the values of your parameters. So first, usually we will define some the computational process. Also, we got maybe input 1 TF the placeholder. So here this placeholder also is a float. And the name of this, I give it a name of this placeholder maybe is also input 1, and we can define another input 2. Maybe this time input 2 is no longer no input, but node 2. Node 2 here this time this node is a variable, and the initial value of this variable maybe 2, and the output node, we will define the output node as output node 2. So output node that equal to also multiply input, multiply input 1 with node 2, and give it a name. Usually we will give it a name. So the name for this out2 maybe is output. Okay. Final output. So that is a computational process. And then we need to start the session. So start a session, use TF the session as says, and then we define variables. So the first thing is to initialize these variables, and here we use system run to initialize, also global initializer to initialize the variable. And the second thing is here we define result 2. So for this result 2, we use system run, also use system run. And in the list, we need to identify which node you want to check. So here the destination maybe is here, that is out2. So I want to check the value of out2, and then we use dict equal to its dictionary. So dict here we define placeholder, so we need dict. We need to feed some value into this placeholder. So the value of this input 1 maybe equal to 7. Yeah, equal to 7. There's no there. And that is the process. So here, if we want to save the model, that means we want to save the structure of this node. That is the structure. We got input 1, we got node 2, we got output 2, how they connected to each other. So so how they connect to each other, and we want to save the values in node 2 out. We want to save the values and the relationship of these nodes and edges. So we will use save models. So to save models, always we would use command like this. We will use tf.train here. No. tf.train.saver. So we define a saver, and here, usually after or during the training process, we can use this saver. The saver we defined, saver the save to save our models, save our structures, and save our weights. So here the first argument is sys, that is this session, and then followed by the address of your where you want to save your model. So maybe we want to save our model. Wait a second. We can define a new folder. So here, what happened? We can, okay, we may save our model log. We may save our model here, that is log, and the name of your model, give it a name. So the name of our model will be taste model, and it's a checkpoint. So hopefully it's no error. Has no contribute saver. Sorry, it should be capital S. Okay, so we use this line and this line to save our model, and now we can check if this checkpoint here is a taste models checkpoint. This index is meta, and I will explain what does these files mean later. I will explain later. So here is the basic grammars to save our model. We use these two lines, tf.train saver and saver.save to save our models. Oh, here we forget to print our result. We can have a look at our result. So here, result 2. So that is the result 2. Result 2 equal to 7 times 2. No, 7 times 2 equals to 14. Okay. So that is the process to save the model. And the next question becomes like, as soon as we save the model, what if next time I want to use the model directly? So how to restore our model? So how to reload our model? So next cell we're gonna explain how to reload our model. So to reload our model, first use start a session. Same, we need to start a new session as this. So to restore the model, also first we need a saver. So the saver is just like an assistant to help us to save models or restore models. First, the saver. So everything related to model save are in tf.train this module, and then here we get a method named input meta graph. That is, we will load the checkpoint we've saved just now. So here followed by the address of our checkpoint. So this is our saver, and so that means we load the checkpoint. So there's two things we just saved. First is the structure of our model, of our graph. The second is the values of our variable, of our parameters. So next thing we're going to do is we need to get a new graph. Yeah, get default graph. We will get a new graph, and we will restore the structure of the model on this new graph. So here, to restore the model, we will use saver the restore. It will be right. Yeah, saver the restore, and also this session followed by so here we need to restore the checkpoint meta. So this file stored the structure of our graph, and this command, this checkpoint, stored the parameters, the values of nodes. So here we use import meta graph, that is to restore the structure of our graph, and here we use saver the restore to restore the values of this graph. So, and then we can use sys.run, print it directly. And then we can use sys.run to get out to check some values of specific node. So here, if we want to check some values, some node value, so we will use here. This G is the graph. So here's the entire graph. A lot of nodes. So which nodes you want to check? We will use G the get tensor by name. No, not get tensor. It should be get tensor by name. Yeah, get tensor by name. So which node you want to check? So we will use graph, this default graph dot get tensor by name. So the name of this tensor maybe is this final output, and only one node. And then in this graph we got a placeholder, right? We got a placeholder. So also we need feed dict. Also we need feed dict to feed input values into this placeholder. So here we also get use G the gate tensor. You can follow me step by step. Gate tensor by name and which node that is the input 1. Always we will use input 1 and okay, that is the name of this node. And the input data maybe can make input data this time maybe is 9. So we can run. That is the output. So here is how to restore the model we saved. First, we need to load the checkpoint. We need to note the checkpoint. That is a meta file. The meta file stored the structure of this graph, and then we need to get a default graph, a new graph, an empty graph, and then we need to restore the graph, restore the structure of the graph, and also the values in the graph, the values of the variables in the graph. And then,
can you kindly zoom in your screen?
Okay. Is that okay?
A bit more, please.
A bit. Okay. Okay.
Also, if you could show the last line, this line number 6 until the end.
Okay. Okay. This is this line number 6. I will explain again. So here we start a session. We restore the graph by sever the restore and restore the structure of the graph and also the values of this graph, and we can use sys.run to get some values from the graph. So here, I'm not sure if you remember the graph we created. Here is our graph. We got placeholders and we got variables. So this time, this variable, we don't need to initialize this variable because this variable will already have some value. So here we only need to, maybe we got placeholders, right? We got placeholders. We need to input something. So here, we need a dictionary to feed input values into this placeholder. So where is the placeholder? You need to identify where is the placeholder. You need to recognize, tell the computer where you want to input the value. So we will use graph the get tensor by name. So I want get tensor by name, and the name of the tensor is input 1. Here, input 1 colon 0. That is the real name of this. That is the real name of this node, and the value we're gonna input is 9. So here is the value we want to feed into the placeholder, and which is the value, which is the node you want to check. So here is a value I want to check. Here is a value I want to check. That is also G, the graph dot get tensor by name. Get tensor by name, which value you want to check. Of course, the final output value is the node I want to check. So that is this session.run. And we can check the final value of the output is 18. So that is 9 times this variable 2 equal to 18. So that is the process to save model and restore models in TensorFlow.
I'm getting the error in the last line. I don't know why.
You don't know why. Maybe you can screenshot your arrow and also your code. The last night, your arrow and your code, send it to my email and I will respond.
Can you please go up?
Go up? Yeah. Maybe I will give you some time to try on your own computer.
Okay, so here on line 11,
11.
You are saving this model, right?
Yes.
So when you say, like when you run this command, two things are saved. One is the graph and second one is the value, right?
Yes.
Okay, so when then you are trying to restore this model and then you send values through feed_dict. So are you trying to like overwrite the previous values? Is the first time when you store this model?
You mean overwrite the previous values?
Yeah. You're overwriting the previous.
No, actually, for
I just want to understand that when you say that, like, you know, in this line, saver.restore, when you say restore the values of the model, what are these values gonna be?
Yeah, that is, so the values would meaning be the values of these variables. So here we got variables.
Okay.
So we will save the value of the variable. If we can try, if there's no variable in your graph, can we save the model? Maybe we change it to a constant. Okay. And there will be at least two variables have the same name. I will click all the output. Okay, we can try. TF is not defined. We need to define TensorFlow, import TensorFlow, and then we can try. There's no variable to save. So the value we save is the value of these variables.
Okay, I got it. So when we are restoring it, then we are actually sending it the input values. The variable stays the same that we saved initially.
Yes. Yes. For example, these placeholders, we feed the placeholder into the graph here. But the next time when we restore the model, we also need to feed the value into the placeholder. It will not save the value of this placeholder we feed into.
Okay, so basically in case of neural networks, these variables would be the weights and biases. So what we are essentially doing is to store the weights and biases so that we can reuse it the next time, right?
Yes.
Okay, thank you.
Okay.
Can I ask why you put a dot after 9 and 7?
9 and 7?
Yeah, on the line number 9, you have written input 1 at the end, yes. 7, and then there's a dot. Why?
Yeah. Dot means it's float. If there's no dot, it will make the data type as maybe int, not float. So here I use dot because here this variable is float, and here this input is float. So here I will use 7 dot to identify its float 22, not an int type.
Okay, thank you.
Okay.
Can you give this save model a quick review so that we can connect or relate what's happening in the beginning and what's happening when you are reloading the model and giving its initial values?
You mean give a quick review of the entire notebook?
No, a save model only.
Okay. So we will go through again. So first, we define the computational process, right? We got one input, and this input is a placeholder. So This is a placeholder. And then we define a variable. We need variables so we can store the model. So here we define a variable, and the training process is the input 1 times node 2, the placeholder times a variable, and here got the output. That is, you can view this node 2 as W and this input as X. So here the function we defined actually is Y equal to W times X. No, not. So input 1 is X, that is the input value, and W is this variable as weights, and Y is the output of this model. So here is the process. Here is a graph. And improve it? Yeah. If we want to train, if we want to see a model.
And the value of this.
Where is the BIOS? Here BIOS equal to 0. You can define a constant as you can define another variable, maybe as node 3. Here node 3 is a variable and it's a BIOS. But here we assign the BIOS as 0. And here is our model Y equal to W times X. And here if we want to define, if we want to save our model, we will use method from tf.train. This saver, okay, here is a saver like a assistant to help us to train models. So here we can run the model. So we can use session.run to run the model. We define variables. So the first thing when we start a session is to initialize this variable. So we use global variables initializer here to initialize variables. And then if we want to check the value of some of the output, we need to use this sys.run, and the first is a list. The first argument is a list, and in the list we need to input the node you want to check. Here we want to check the value of out2, and we need predict because there is a placeholder. We need to give something to this placeholder so it will compute. And here we use predict. It's a dictionary. So the key is the node, which node. So that is the input 1, this placeholder, and the value here, the value is 7. And we can print the output of out2. So here out2 is equal to 14. So that you can view that is a process to check the values, and we can save the model.
I have a question.
Yes.
What is this tf.variable 2.0 in node 2? I still didn't get it.
TF which line?
This line 2. Line 3 in your code.
Line 3. Okay. This is a variable.
Yes. So what does this 2.0 means?
It's 2.0 means the initial value of this variable.
Okay. But like you gave it some kind of a default value.
Yeah, it's a default value, but like I've said here, this variable usually are weights and BIOS, and the aim to train a model is to find the proper weight and the BIOS to minimize the loss function. So here, this variable means the W weights.
Yes. Okay.
Yes. We give it some initial value, so it will can compute, make the first prediction.
Okay.
Yeah. So here, you can view it as a training process, but actually it's
I
not
have
a
a question.
Yes, please.
Can you kindly tell me that in result 2 in line number 10, we are giving we are we are running for out 2, but when in the feed dictionary we are giving the value of input 1, but if we want to give the value of node 2, can we do it here, or it should be changed by in line 3 only?
You mean give value to out to?
I mean in line 10.
Yeah,
when we are we are running the session for out value, right? Okay.
Yeah.
I'm myself confused. I mean that if in this line, in line 10, can we give the value of node 2 as well, or there is some specified pattern for
Node
this?
2 as well. No, we can only feed. We can only feed.
Input.
Yeah, to placeholder.
Okay.
You can.
And very node 2 value can be given to out 2. That is automatically in the result. Okay.
So we will use feedict to give values to placeholder.
Only to inputs. Okay, I got it. Okay.
Yeah.
Thank you.
Yeah, and here, this line is a 9 to save models. Here we define a saver and the saver does save. Here, this is a session. This is first argument, and the second is the location, is the address you want to save, where you want to save your model at a checkpoint file. So here we save our model. So next cell we use command to restore our model, use some code to restore our model. So to restore our model, first thing we're going to restore is the structure of the model. So this file, this meta file, stored the structure of our model. So we will use also tf.train import meta graph to restore the structure of the model, and then we need to get a empty graph. Here G is empty graph, and then we start a session, use saver.restore. Here is a saver. Here is a saver. So there are a lot of nodes, and we will use saver.restore to restore the values to corresponding node. And then we can also use session.run, also feedict to feed some values into the placeholder, and we can also check values of some nodes here in this list. So we always use get tensor by name. We will get tensor by name. So which node you want to check? I want to check the output, final output node, and here I want to check. Here I want to feed the number 9 into the input 1 as a placeholder. So we can print the final output. That is the value of final output, this node. That is 18. So that is a process to save the model and restore models. Any other question? So after the class, I will send these GPL files to the local manager, and they will share these files to you guys. If there's no question, maybe next we're gonna talk about, okay, that is the key chapter. That is the key chapter of our training session as the overview of deep learning. First, we can have a view of this agenda. We want to first that this first section, we can talk about something related to machine learning. So some commonly used machine learning algorithms, and why is hyperparameter, why is parameter in model and why is validation dataset, why is test dataset, and why we need the validation dataset. And also, these three sections are not that important, so we will not talk about these three sections in details. And also for the exam, you can just ignore these three sections. You will not find any questions from this exam. There is no question from these three sections. And so the second part is officially the overview of deep learning. We're going to talk about the CNN convolutional neural networks, recurrent neural networks, and get the how they work and how to train these neural networks, and why these neural networks would work. So that is the agenda. Maybe we can have 10 minutes break, and then we will continue to talk about the machine learning part.
I have a question.
Yes, please.
Will you share this Jupyter notebook file with us, which we did today?
After class, I will immediately send these Jupyter files to your local manager, and I will ask him to share to you guys as soon as possible.
Thank you.
Okay, thank you. Okay, we will start. So first, maybe today we're gonna talk about some terms in machine learning and also some commonly used machine learning algorithms. So first, the first topic is learning algorithm. So what is learning algorithm? So this diagram or this picture shows us what is learning algorithm. We can compare the learning algorithm of machines to the learning process of human beings. So for us human beings, so how to learn something. So usually we got some specific task, maybe for example image classification task to identify whether it's a dog or a cat, and or to identify whether it's a person or a bicycle, and we got a task here. Usually for the first time, when we encounter when we encounter some new task, we may how to solve this problem. Usually we will learn from our experiments. We will learn from our experiments. So we got a task and we will learn from our experiments, and then we will give some conclusions of this task. We will have some solution of this problem. So that is our training process to solve a problem, to complete a task. And for a model, here, task for us human beings, just like learning algorithms for model, it's model follow some specific principles or has some specific strategies. So here as a model, actually some mathematical functions, equations. So ask to human being just like a learning algorithm, just like algorithm for models, and experiments to us human beings, just like data to algorithms. So the algorithm would learn from the data, would induce some nodes from the data, and then it can understand, it can solve some specific problem. So here is the comparison of the learning process of human beings and the learning process of a model. So for us human beings, a new problem come and we will induce some node from the experiment, and we will make some prediction, or we will get some solution, found out some solution of this specific problem. And for models, when a new data come, first the model are trained model. So we need to train the model with historical data. So for this historical data are training data. We always call it training data, training data. So we use training data to train the model, so the model can induce some nodes from this training data set. And when some new data, some new similar problem come, and they can make some prediction. That is the learning algorithm. That is the learning process. We need training data to train the model, and the new data always are some test data. So we need a test sample into the data, and the data make prediction according to the laws from the training data. So that is the learning process. So there's some, next we're gonna explain some basic terms and concepts in machine learning. First, we need data, especially deep learning. It's data-driven algorithms, and we need loads of data to train the model, to make the model work. Just like we need a lot of experiments to make us maybe Sweden. And here the training data set for machine learning learning models, usually we can divide the dataset into training dataset, test dataset, and also validation dataset. First, let's have a view of what is training dataset. So as we've mentioned before, training dataset is the dataset here, historical dataset. We use training dataset to make the model intelligent, to make the model learn from the data automatically, and then we use test set as input to test if the model works. So that is dataset, training dataset, test dataset, and later we will introduce the validation dataset and the function of validation dataset, the usage of validation dataset. And here are some basic term, some basic concepts. So the first concept we can talk about is the capacity of a model. So the capacity of the model refers to the ability to fit functions, to fit data. So capacity of the model is the model's ability to fit data. So usually we got here underfitting, overfitting, and here the picture in the model is the example that the model just fit right. So first question is, why is underfitting?
It is not well trained.
It is not well trained. Yeah. Why it is not well trained for underfitting model, underfitted model?
Because of the weights and because of the parameters that are chosen, they're not sufficient.
Yes. So for the underfitted model, for this underfitted model, always like maybe the samples, the training dataset is the nonlinear dataset, nonlinear samples. Actually, we need curves to fit this dataset. But here, the model we use are linear models. So linear models cannot solve unlinear problems. So that means the model is too simple compared to the dataset. So it will cause underfitting problem. It fails to learn the features. The model is too simple, and the dataset is not that simple compared to the model. The actual problem, the actual solution is a nonlinear solution. But here we want to use a linear function to fit some, trying to figure out some nonlinear solution. So that is underfitting problem. That is the capacity of the model is too low or is not sufficient compared to the dataset. And so here another problem, another term is overfitting. So what is overfitting? Why? Yes, please.
It's overtrained, and it is the information that we have provided is more than sufficient.
Yes, thank you. So that is overfitting. Overfitting means it's overtrained. We trained the model. We trained the model over and over and over times, over and over and over again. So it will learn some noise. It will remember everything in this training data set. Just like this, it can learn some even noise from the training data set. That means the model is too complex compared to the dataset, just like a student even remember every single words in our textbook. So but it fails to induce some noise of specific problem. That is overfitting problem. It's overtrained. So here is an example of overfitting model. It will be like this, and here, this function, this curve is just fit perfectly. It fit the trend of the samples. So that is underfitting, overfitting, and just fit right.
So the overfitting model will be, it will be like biased to the current data set, and if we give it a new data set, the results will be not that good or erroneous.
You mean the overfitting problem will be
The overfitting, yeah, the overfitting that we just talked about. So I guess it means that if that the model is very much biased to the data set we have inputted.
The overfitting means the model makes very high accuracy for in the training data set, but a roughly low accuracy in training data in test data set. For example, here. Here we trained also for image classification model. So in training data set, the accuracy maybe is 99%. It's 99% if it fits perfectly. And but in test dataset, the accuracy is just 17%. So that is an example of overfitting problem. It fits perfectly in training dataset, but it fails to predict proper labels in training in test dataset.
Okay, so it cannot comprehend the new data.
Yes.
Oh, okay, thank you.
I want to ask that if overfitting and underfitting are inverse to each other.
Inverse feature.
Like if we more overfit the data, that underfitting will come less, like that.
More overfitted data, underfitting will come on nurse. I didn't get your question.
I am asking that overfitting and underfitting are inverse to each other. Like
inverse
if we more overfit the data, it will be less underfit.
If
Maybe I can answer that question if you don't mind.
Yes, please.
Okay, so it's not the data that is overfit or underfit. It's the method you are using, the machine learning method. So if you're using the wrong method, so it would be what do we call it? An underfit model. And if you use so much training of the model using the same data again and again, so it will be an overfitted model. I guess if it answers your question.
Yeah, to talk about overfitting and underfitting, we are talking about the overfitted model or underfitted model, not samples. So, yes, please.
I can answer, please.
Yes, please.
Okay, so you said whether underfitting or overfitting are inverse. If we think about it, of course, if a model is overfitting, it means that it's kind of underfit. And what is underfitting? Underfitting is not being able to generalize to new data. So when the model is overfitted, of course, there is gonna be underfitting. And if your model is way too underfitted, then we cannot necessarily say that it's overfitted, but we can say that it's kind of not generalizing well. In the overfitting case, we can say that it's so much generalized to the training data that now it cannot see the general trend in the.
So I would like to add, like, for example, underfitting would be something to, you have a problem, to solve that problem, you need some time. So let's say you're given a complex problem, and to solve that problem, you're given maybe very less time, maybe 2 minutes. But if you're given very simple question, simple problem like 2 + 2 is 4, and for that you are given a lot of time, for example, maybe 2 days, 3 days, this is called overfitting. So you're using lots of resources to solve something that is that can be done in less time. So this is what is overfitting and underfitting.
Okay, thank you so much. Okay. So this is overfitting and underfitting. When we talk about overfitting, any other? Anyone wanna add any other comment? Okay. That is underfitting and overfitting. We're talking about the model, the complexity of a model and the data set. So this is an example of underfitting. This is an example of overfitting. The model is too complex, and for the underfitting problem, the model cannot generalize, cannot fit the samples correctly. So that is overfitting and underfitting. So these two, wait a second. Oh my God, my computer shut down for no reason. Okay. And then we continue to talk about some other terms like the accuracy, the error rate. These are very basic terms and very easy. So we will directly jump to some commonly used machine learning algorithms. So to talk about some specific machine learning algorithms, so first let's have a view of the types of machine learning. So the types of machine learning, we can divide it into 4 types we mentioned in the first lecture. 4 types: supervised learning, unsupervised learning, semi-supervised learning, and reinforcement learning. So we've talked about these 4 types so many times. And for supervised learning, the model would learn from data that is labeled. So we will learn from this labeled data and trying to make prediction, as that the label data and the prediction is make no difference. That is the target. So for unsupervised learning, the data we use to train the model are unlabeled data. We only got data samples with a lot of features, but no labels, So generally the aim for supervised learning and typical example is clustering. So for supervised learning algorithm, usually when the model will try to find the similarity between samples, and they are trying to find cluster similar samples together. So that is unsupervised learning. And for semi-supervised learning, we train the model both with labeled data and unlabeled data. And I've already gave you the example of semi-supervised learning. And why we need semi-supervised learning, that is because the data labeling is very expensive. is very expensive. For example, for especially for some medical images, for these medical images, CT, this kind of X-ray, this kind of image, only doctors can label this data, and to train a deep learning model, we need a lot of medical images, and the doctor should spend their time to save lives rather than label these images. So the data labeling will be very expensive, and they will spend a lot of time and labors to label these data. And so we can use semi-supervised learning to train a model for data labeling to label this unlabeled data, and then we can do supervised learning to train a new model for specific tasks. And also, we mentioned about reinforcement learning. We got an agent and environment, and the agent will interact with the environment. It has an action it will interact with the environment, and you have a reward or punishment, and you will adjust themselves. It will update the status of the agent according to the strategy and according to the reward and the punishment. So that is reinforcement learning. So here we just have a review of these 4 types of learning algorithms, and then we may continue to talk about some specific learning algorithm. Maybe the first learning algorithm we would talk about is linear regression. So what is linear regression? So maybe another question is, why is regression?
Regression is basically when our labels are continuous data.
Yes.
Linear regression means trying to fit a linear curve to our training data.
Okay, thank you so much. So for regression, actually, the tasks for machine learning, we can divide this task into 3 types. First is the regression task, and first is the regression task, and the second is classification task, and the second is clustering. So we can divide these.
The second is not visible.
Oh, pardon?
Your second screen is not visible. I get your Word file.
Sorry. Here, we can divide the task of machine learning into actually 3 types. So the first type is regression, as one of, I cannot remember, the lady mentioned the regression task is the output is continuous data, and for classification task is the output is not continuous data. So the task can be divided into 3 types. And for clustering are like we mentioned in unsupervised learning, we want to find the similarity of samples and cluster similar samples into the same cluster. So that is the 3 types of machine learning tasks. So first algorithm we want to talk about is, I will write down here, linear regression. So linear regression, of course, is a regression problem. It's a regression problem. So the prediction, the output of linear regression is a continuous data, and here why is in linear regression? Because when you use linear functions to make predictions. So for example, typical example is y equal to w times x, w times x plus b. So this is a linear function, right? This is a linear function in 2 dimensions, and this is a linear function, and we use this function to do regression programs to trying to find out the trend of the samples. For example, the typical example is we use a lot of samples to predict the price of the house. So for example, yeah, here we collect a lot of samples. Here is sample 1. And so every sample have a lot of features. So for this data set, so house got arrows, real arrows, and the size, the number of the living room, and the second feature, and also the location of the house is very important. That is a feature. And also, okay, just 3 features. Okay, first, the size of the house. For example, maybe the year of the house. So for example, the sample 1, the size of house may be 300, and the number of bedding rooms of this house may be 2, and the location of the house, we will use a number. It can be like 0 or 1. 0 means the location is not good, and 1 means the location is very good of this house, and the year may be 2005. Okay, this is the first sample, and we can collect another sample like 200 and 2 and 4 and 0 and 2010, and we can collect other samples. So here we use linear regression. Linear regression is a supervised learning algorithm. It's a supervised learning algorithm. So the sample we collect should be labeled sample. So here the labels of these samples are price. Price. So for sample 1, the price may be, I will use $1,000, and here the price of the sample 2 maybe is $2,000, and here sample 2, it got a size, number of bedding rooms, locations, years, and labels. So we collect a lot of sample, and these are training samples. We want to use this training sample to train our model. Here, model actually is functions. So here, this is a function. This is an equation. We would want to use this equation to generalize to these training samples, to fit these training samples, trying to make predictions of these samples. So for example, for this linear regression problem, here we got 1, 2, 3, 4 features. So the 4 features. So here the equation will be x1 times w1 times x1 plus w2 sorry, W2 times x2 plus W3 times x3 plus W4 times x4. 1, 2, 3, 4. Yeah, and plus BIOS. So we will use this equation. So here, this x1 means the first feature, and here x2 means the second feature, number of bedding rooms, and these x3, x sub 3 means the location of this room, and here x4 means the year of this room with BIOS. We will use this equation, and when we train the model, that means we want to find the proper value of x1, x2, x3, x4, and the BIOS B. So if we find the proper value, of these weights and the BIOS, we can make a prediction when some new data comes. So that is linear regression. We will use linear function to do regression, and the values, the predictions are continuous. So that is linear regression. And next algorithm we're gonna talk about is the logistic regression. And for this machine learning regression, like linear regression, logistic regression, decision trees, and support vector machine, we will not go into very detail to talk about this equation, to talk about how to find these parameters, how to train these parameters, and the loss function of these parameters, because we will spend a lot of more times. We will try to spend more times to focus on the deep learning part. So here is logistic regression. And okay, one thing I need to mention about the linear regression, we use this kind of function to train on these samples and then trying to make a prediction. So when we train the model, that is when we train this equation, that we're trying to find the proper value of weights and BIOS. So how can we know if the model works fine or not? How can we evaluate the performance of this model? So always we would use a function, we call it the loss function. That means here we make a prediction. So for the first time, the weights and BIOS are randomly initialized. For example, the 1, 1, 1, 1, all equal to 1, and the BIOS may be equal to 0.1. And here it can make a prediction. For example, we input the first sample, it make a prediction, and maybe the prediction is the prediction of for the first time is maybe 90. So here we will compare the prediction with the actual label. So we will compare how to evaluate the difference of the prediction and the actual label. That is minus. We will use loss function. So usually for this, we will use mean square error. That is, we will compare. We will y1 minus the actual label. And square. So this is just an example to evaluate the difference of prediction and the actual label. So we will use loss function. So loss function is a function to judge the difference, to evaluate the difference between predictions and actual labels. So the goal, the ultimate goal of the training process is to minimize the value of this prediction of the loss function. That means the prediction of would be equal to the actual label. That is the goal, but always we will not find the local global minimum of the loss function. So the goal of our training process is to minimize loss function, that to make the prediction equal to the actual label. So that is the loss function, and that is linear regression. We will use a linear function to predict some continuous numbers. And next algorithm is logistic regression. So here we can have a look of this logistic regression. This is the equation of logistic regression. So for logistic regression, we will use a sigmoid here. This is the sigmoid function. This is function. So one thing we need to mention is that also logistic regression is also a is also a supervised learning algorithm. It's a supervised learning algorithm. So we will make some notes. It's supervised. A supervised learning algorithm, and it's logistic regression. The name is logistic regression, but it's an algorithm to solve classification task. So it's an algorithm for classification task. So that means the output is discrete. So for logistic regression, it's a model for binary classification. That means the output will be will be 1 or 0. So the output will be 1 or 0. So for example, here is the sigmoid. Here is this sigmoid function. So the input will be from, so we got input x. So the sigmoid function would map any input to the interval 0 to 1, would map anything to 0 to 1, to 0 to 1, just like the probability value. So here, for example, if we input x, if x is if x is larger than 0, if x is larger than 0, so the output value, of the sigmoid function will be larger than 1.5. So here its label may be 1. So if x is smaller than 1, and the output value of the sigmoid function is smaller than 1.5, and the final label, the prediction label of this sample is 0. So that is logistic regression. It's a supervised learning algorithm, and it's for binary classification task. So that is linear regression and logistic regression. And
yes, Kelsey, sorry, I think there is some mistake in the this logistic regression equation.
Yeah, yes, please.
The equation is e की power wx plus b over 1 plus e की power minus wx plus b. It's minus down.
Down? You mean here?
Yeah. Yeah, e की power minus wx plus b. I think. You can verify first. Yeah, here. Negative. Yeah.
Here is
No. In power plus e. Yeah, e की power minus negative. Yeah. Then starting bracket. Yeah, wx plus b in bracket. You can put wx plus b in bracket.
Okay.
Yeah.
Okay. I will check.
Yeah.
Okay. So that is regression, and then the next commonly used algorithm we're gonna talk about actually is clustering algorithm. And wait a second. So here the third algorithm we're gonna talk about is k-means. So k-means is a clustering algorithm, and for clustering, the aim for clustering is to find the similarity of samples. So here k-means. So why we need to mention k-means this clustering is here. This k in its name is a hyperparameter. So here k means the number of clusters, the number of clusters you want to cluster.
Yes, our screen is not visible.
Okay, here the k-means. So here this k is the number of clusters you want to cluster. For example, if k equal to 3, I will cluster this data set into 3 clusters. So that is k-means. Okay, what does this mean? We will explain. So first, let's have a look of the steps of k-means. So let's have a look of k-means, maybe step by step. So for k-means algorithm, so here k is a hyperparameter. We can call it a hyperparameter. And what is hyperparameter? So actually we can divide parameters for machine learning or deep learning models into 2 types. The first type is parameters for the model that can be trained, that can be adjusted by the model itself, just like weights and BIOS. The model would find the proper value of these parameters during the training session, but there are another type of parameters, we call it hyperparameter. So hyperparameter is a kind of parameter that the model cannot learn from the data set. So we need to adjust the parameter manually. We need to adjust the parameter according to our experiments, or use other method to search for the proper value of this hyperparameter. So that is parameter. We can divide the parameters of a model into 2 types. The first is parameters that can be learned, that can be the value of the parameter can be learned during the training process. The second type is hyperparameter. We have to define the value of these hyperparameters. The hyperparameters can be, the value of the hyperparameters can be found manually or found by other method, other searching method. So here K in KNN is a hyperparameter, and KNN of course is a clustering problem. It's a clustering problem, and of course it's unsupervised. It's an unsupervised learning algorithm. So for k-means, we will go step by step to explain how k-means work. So for linear regression, we explain one term, that is loss function. What does the loss function mean? And for k-means, we will go step by step. So first step of k-means, actually here k is a hyperparameter. So the first thing we have to choose the number of k. Number of k, that means how many clusters you wanna, how many clusters you wanna cluster, how many groups you wanna cluster, and that is the first step, step 1. And the second step is, okay, now I choose k equal to maybe here k equal to 5. K equal to 5. So I decided to cluster all the samples into 5 groups. So next step is step 2. Usually we would randomly choose k points as the central point of each cluster, of each group. So that is the second step. We will randomly choose the central point of every group. So the second step, and the next step is step 3. So the goal of step 3 is to compute the distance between, for each sample. For we got a lot of samples, so for each sample we will compute the distance between the sample to every central point. So I will come. There are I choose one sample, and we will compute the distance of the sample to the first central point, to the second central point, and to the fifth central point, and compute the distance, and then assign. And then we will assign the sample to the closest group. So which central point is the nearest central point? So I will assign the sample to the nearest group. So that is the third step. So after the third step, I will draw. So after the third step, every sample would have their own group. For example, here is the central point, here is central point, here is central point, and here is central point. 5 central points. Okay, so after that, every sample will have their own groups. Like this. Okay, only. Okay, for example, here k equal to 4. So after the third group, our sample will be like this.
But Kelsey, there are 5 groups. K equals to 4.
Yeah, maybe here k equal to 4, and our, I will write down, if k equal to 5, it will be like this. Here, if k equal to 5, so after the third step, our data set will be like this. So the next step is, what is the next step? So usually the step 4.
We are starting clustering from 0, 0, 1, 2, 3, and 4. We are counting from 0.
Counting from 0. You mean?
Yeah. That's why you have pointed k is equal to 4, and there was a 5 cluster. So that's why I'm saying you are starting from 0.
No, k equal to 5. K equal to 5, and the k is a hyperparameter. The first step is to choose the number of k. So here it's a hyperparameter.
6 clusters.
1, 2, 3, 4, 5. Sorry. Okay. Oh, there are 6 clusters. Okay, erase. Oh, okay, here are 5 clusters. Sorry.
Indiana.
Yeah, there are 5 clusters. So after the third step, so every sample will be clustered to corresponding group, the nearest group. So the next step is we gonna recompute the central point again. Of each group. So we're gonna recompute, we're gonna update the central point of each group. How to update the central point of each group? That is, find the mean value. That is to find the mean of these values, a mean of these samples. For example, for this group 1, for this group there are 1, 2, 3 samples. So here, this is not a sample. This is not a 1, 2, 3. We got 3 samples. We got 1, 2, 3 samples. And to update the central point of the sample, we will take the average coordinates of these 3 samples. Maybe here is the updated. This is the updated central point for this group. So for every group, we will update the central point. We will update the central point like this. So that is the fourth group. So after the fourth group, we will repeat the third group and the fourth group again and again. That means after updated the sample point, and we will assign all the samples to the closest group, So, and then we will recompute the central point. We will update the central point. And so when should we stop? So there are different rules stopping criteria. There are different stopping criteria. One typical stopping criteria is maybe for this step 4, when we update the central point, we find that the central point stays the same. So that means the central point do not change. If the central point do not change, we could stop. That means we cluster all the samples properly. So that is the first example of the stopping criteria. And so another example for stopping criteria, maybe when we do maybe step 3 to assign all the points to the closest cluster, we found out all the samples. All the samples remain in the same group. So at that time we can stop training, we can stop update. So that is KNN. So next time when we input some new value, we can maybe here we input a new value, here is a new value, and maybe we will do cluster, the new value belongs to this cluster. So that is the testing process. So that is the K-means. Maybe that's all for today. And tomorrow we'll continue to talk about some machine learning algorithms, and then tomorrow we will mainly focus on the deep learning part to talk about CNN, RNN, LSTM, and again. So that's all for today. Any question?
I have a question about k-means clustering.
Yes.
Let's suppose that our data is too much scattered. So how will it perform better? We will have a lot of outliers in the data.
Pardon, you mean this? Suppose our data is
Scattered.
Scattered.
Yes, there are outliers. We cannot form good clusters of it.
We cannot form good clusters of it. Maybe we can change maybe the value. We can do some feature selection. We can do some data pre-processing to make the data clean, or we can change the value of this K. For example, if we increase the value of this K, and we can cluster these samples properly. Maybe here, if here is a sample, and here the proper value for K may be equal to 6. So here will be cluster the group 6. So it doesn't matter if you can use some data pre-processing, or you can change the value of your hyperparameter to make sure that your samples are clustered properly. Yeah. Any other question?
I have questions for bias, which we use in different algorithms. Can you explain this, since in most of the algorithms or techniques we set it to 0, bias set it to 0.
Yeah.
So what is its importance, and what will be the suitable value for the bias?
The suitable value for the bias, it depends on your task and your data set. So it's the parameter we're gonna train. So usually we make the bias equal to 0 just for mathematical convenience. For example, here, wait a second. Here, if for linear regression, the bias equal to 0, it will be always on the original point. Right.
Yes.
So for this sample, if we don't use maybe methods like data pre-processing or standard, or scale this data, makes the data, the mean of these samples equal to 0 and the standard derivation equal to 1. So we will do standard derivation. We will scale this data, make this data to maybe the distribution, the mean of this distribution equal to 0 and standard derivation equal to 1. So at this time, it is okay if you set the bias equal to 0, because your samples will be located here around the original point. So it's okay to set the bias equal to 0. But
so
if you
you want to say that this regression line will always pass through the 0, 0
region. Yes. If bias equal to 0, you'll always pass 0, 0 this point. But and if you do data pre-processing to scale this data, the data will be always around this 0, 0 point.
Okay. Thank you.
Okay, thank you. Any other question? If there's no question, maybe that's all for today. So we will continue tomorrow.
Thank you. Please share all the material of slide today and yesterday. Previous day, and all the slides. Please share. Because we still have not received anything from your side.
Okay. I will share the Jupyter files, and I already share these slides to you guys, right?
And please guide about that math slides. We did not receive the slides of that you showed yesterday, the updated slides of math portion, and
the updated slides I saw yesterday. Also the blue slides or the white slides.
The white slides.
Okay, you can download the white slides. You can download the white slides in the link. From the link I've already shown you. You can check the emails and click the link. There is a training material link, and according to the link, click this link and you can download the white slides I showed to you yesterday. Or I can send the white slides to your local manager and they will share to you by email. Okay, I will send the Jupyter notebooks and the white slides to you guys. And any other question? Okay, if there's no question, so that's all for today. Thank you so much. Thank you for your patience. Thank you.